Yes, sorry. Related. Yeah. Okay. Great. Well, I'm going to be talking to you today about Reeb dynamics in dimension 3. I'm going to try to give sort of a high-level overview of some results that I think are interesting and some questions that I want to think about while I'm here. So first I want to thank the Institute for inviting me to give this talk and to spend the year here. And now let's get to it. So I'm going to be talking about Reeb vector fields. So to define a Reeb vector field, we need an odd dimensional manifold. And we also need a contact form. And I don't want to go into the technical condition to be a contact form. This looks a little bit opaque maybe to non-specialists, but if you're not a specialist, you should just think of this as an odd dimensional analog of a symplectic form. And anyways, for the purposes of this talk, the manifold is really going to be a 3-manifold, and we really just care about the contact form because it's going to allow us to define Reeb vector fields. So we have a 3-manifold with a contact form, and now we can define a canonical vector field called the Reeb vector field. And what I'm interested in are the dynamics of the Reeb vector field. And this comes up naturally in many contexts. It's related to geodesic flows, autonomous Hamiltonian systems. I think there are some other members here who might talk more about that, but if you're a non-specialist, we have some vector field and we want to better understand its dynamics. So seminal conjecture about Reeb vector fields is the following conjecture due to Weinstein from the late 70s. So what Weinstein conjectured is that if I have a closed manifold with a contact form, then the Reeb vector field always has at least one closed orbit. And a closed orbit of the Reeb vector field is called a Reeb orbit. So that's really what we're going to be talking about today, Reeb orbits. So one thing that's great about this conjecture is there has certainly been some progress. So one main result is due to Viterbo in the late 80s. So he showed that this is true for closed hypersurfaces of contact type in R2n. So again, I want to take a high-level overview. So I'm not really going to say what the definition of a hypersurface of contact type is, but this is the type of result that's particularly nice if you're interested in the applications to autonomous Hamiltonian systems. Another very important result is due to Hofer, who showed that the Weinstein conjecture holds in dimension 3. So I'll start with the third condition, because that's certainly the most accessible to non-specialists. So if your manifold is diffeomorphic to a 3-sphere, then it's true. Or if pi2 is non-zero, or if the contact structure is over-twisted. So again, I throw that in there for specialists. And recently, Taub showed that the Weinstein conjecture is just true in dimension 3. So that's really the starting point from where my talk and the results I'm going to describe starts. Okay. So for where I'm going, it'll actually be convenient to sketch a proof of the Weinstein conjecture. And again, if you're a specialist, these types of arguments seem very standard. If you're a non-specialist, this is going to seem completely wild. But the ideas here are certainly not due to me, but also not even due to Taub's. They really go back to ideas coming from Flohr and Hofer and Eliashberg and others. So we're going to actually come up with a 3-step plan to prove the Weinstein conjecture. So what's our 3-step plan? So first, we're going to try to define a chain complex that's generated by Reeb orbits. So again, remember, to define the Reeb vector field, we need a contact form. And that's sort of important. We have lots of different contact forms, and they all define different Reeb vector fields. So we're going to pick a contact form. We're going to define a chain complex that's generated by Reeb orbits. Step 1. Step 2 is that we're going to pick our chain complex so that the homology of this chain complex is an invariant, that it only depends on the 3-manifold and not on the contact form. And obviously, one can imagine that this is going to be hard. I mean, there's certainly a lot of art in picking a chain complex differential so that the homology is an invariant. Because again, what you want to think of is that I have lots of different contact forms, and they all have different Reeb vector fields, and they all have different Reeb orbits. I mean, some might have only 2 Reeb orbits, some might have infinitely many embedded Reeb orbits, and we have to be very careful about this to get things to work out. And now that we know that it's an invariant, we can hope to compute it by, for example, taking a very nice contact form and doing some computations. We want to show that the homology of this chain complex is non-zero, and hence that there's a Reeb orbit. So that's our general program. And the cool thing is you can actually get this to work. So how are we going to get this to work? Well, let's remember what step 1 was. So we want to define a chain complex that's generated by Reeb orbits. And there are lots of ways to do this. Professor Hofer sort of has many ways of defining such a chain complex. But I'm going to talk about an idea due to Michael Hutchings, which is embedded contact homology. So this is the homology of a chain complex generated by certain finite sets of embedded Reeb orbits together with non-negative integers. So you want to think of this non-negative integer as roughly a covering multiplicity. The Reeb orbit here is embedded, but if you're an orbit, then you can go around multiple times, and that's roughly what this non-negative integer is measuring. And remember, I said there's a little bit of an art to picking the chain complex differential correctly. So for the chain complex differential, I'm going to want to count J-holomorphic curves in the symplectization. This is, again, one of these things where I want to keep things fairly high level. If you haven't seen a J-holomorphic curve before, this will sort of course, seem completely opaque. I mean, roughly, you can think of these as like holomorphic curves. And this idea, again, goes back to work of Gromov and work of Professor Hofer and others. I mean, but the characteristic thing about embedded contact homology is this ECH index. Sort of many people have studied many ways of counting J-holomorphic curves, but in ECH, the idea is that you want to count ECH index 1 curves, which is the ECH index is a topological quantity that really uses the fact that R cross Y is a 4-manifold and involves sort of a certain intersection form type thing, and it only depends on the topology of the curve and not on any of its analytic properties. And it's the key non-trivial component of the definition of ECH. So that's good. We have a chain complex, at least in principle, but one still has to show that the differential squares to 0, and this is a result of Hutchings and Taubes from several years ago. So that's sort of step 1. We have a chain complex that's generated by Reeb orbits. So now step 2 is really what got me excited about this area. So we want to show that the homology of this chain complex only depends on Y and not on the contact form. And this again seems like it could be, quite hard. How on earth are we going to do this? Well, we have a really great theorem due to Taubes, which says that there's a canonical isomorphism of graded abelian groups between embedded contact homology and the Seiberg-Witten-Floor cohomology defined by Kronheimer and Moravka. So I don't want to say a ton about Seiberg-Witten theory here, but I do want to make a few remarks. So the most important remark for our purposes is that, as you can see from the notation, the Seiberg-Witten-Floor cohomology only depends on the 3-manifold Y and not on the contact form. So that's sort of why we care about this. Now, you might expect, you could also have sort of why on earth would I expect this to be true? And it's certainly a surprising result. If you're familiar with earlier work of Taubes, on, for example, there's sort of well-known work on what it's called Gromov equals Seiberg-Witten, then Taubes had already shown sort of a closed version of this isomorphism. And this is sort of like a Gromov equals Seiberg-Witten for 3 manifolds and for the non-compact 4-manifold Y cross R. So this type of result is a little bit more familiar if you're familiar with Taubes' work from the early 90s. But this is sort of great for us. So we showed that the homology of this chain complex only depends on the 3-manifold and not on the contact form. And we actually get something else for free too, which is step 3. So remember, non-triviality also seemed very hard. I was saying maybe we have to pick a contact form so that sort of things work out nicely. But actually, that's not true either, because Seiberg-Witten-Floor cohomology, the non-triviality theory, is much easier. It's worked out by work of Kronheimer and Moravka. And they actually show that the Seiberg-Witten-Floor cohomology group has infinite rank as a Z-module, which is already pretty interesting. I mean, so this implies, of course, that ECH has infinite rank as a Z-module. And it also hints that there might be sort of other things going on here, because, of course, to prove the Weinstein conjecture, all we needed was that this had rank 1 as a Z-module. That's not actually quite true for reasons that I don't want to get into, but actually we sort of got more than what we needed to prove the Weinstein conjecture, which is already interesting. So now, a strange thing about my presentation is that this isn't actually Taubes' proof, which just uses Seiberg-Witten theory. So you might ask sort of, why did I bother to waste your time? You're all important people. So why didn't I just explain Taubes' proof? Well, there's a reason for this, which is that this circle of ideas can be used to say more about the Reeb flow. And that's sort of what I'm interested in. So, for example, a result of Hutchings and Taubes from 2009 shows that if you have a non-degenerate contact form, and this is a technical hypothesis that, again, I don't want to get into, but it's sort of analogous to non-degenerate critical points in Morse theory. So if you have a non-degenerate contact form, then what Hutchings and Taubes show is that you have at least 2 embedded Reeb orbits, and at least 3 if the manifold is not a lens space. And then last year, Hutchings and I were able to remove all the technical hypotheses from this. We showed that any contact form on any 3-manifold has at least 2 embedded Reeb orbits. And Doris Hein, who's also a member here, at the same time came up with a completely independent proof of this fact when the 3-manifold is S3. Okay. And so this is a nice result because there are certainly examples of contact 3-manifolds with exactly 2 Reeb orbits, but there's certainly more that one can say. for example, a very celebrated result of Hofer and his collaborators shows that if I have a non-degenerate contact form on S3 giving the standard contact structure, so again, I don't want to go into what the standard contact structure is, but this is a very large class of contact forms, then what they show is that the Reeb flow has either 2 or infinitely many embedded Reeb orbits, provided that a certain technical hypothesis holds. And one might even guess from looking at examples, and I've called this speculation, because I wouldn't bump this up to a conjecture, because I think there's sort of lots more work to be done. But one might even guess, based on looking at existing examples, that if your 3-manifold doesn't happen to be a lens space, then the Reeb flow always has infinitely many embedded Reeb orbits. So that's certainly something that I'm interested in thinking about while at the Institute, and there's a great community of members to think about such questions. But another thing that I've been thinking about this summer that I want to talk about is a slightly different refinement, which is the question of whether or not there's a short Reeb orbit. So one has to make sense of this. And the reason for this is as follows. If I have a contact form, I can scale it. I can just multiply it by a constant, and that's going to mess with the periods of things. So it certainly doesn't make sense to ask, is there a Reeb orbit with period less than or equal to 1? That's sort of not a, well, that isn't a well-posed question, but the answer is no. So we have to sort of make sense of this. So let's define some terms. So we're going to define the action of a Reeb orbit by integrating the contact form along the Reeb orbit. The action of a Reeb orbit, by the way, so again, if you're a non-specialist, if you have a Reeb orbit, then this also gives you the period of that Reeb orbit. So that's why I'm calling this short. If this number is small, then the Reeb orbit is pretty fast. Some might also call this the symplectic length or something like that. And then we want something to compare it to. So we're going to look at the volume of the 3-manifold. The contact condition implies that this 3 form is actually a volume form, so this is a reasonable quantity to define. And we're going to ask the following conjecture, for which I think there is some limited experimental evidence, but this might be optimistic. So the conjecture would say that there's always a Reeb orbit with action less than or equal to the square root of the volume. And the square root here is done so that the constants work out correctly. And this type of thing is familiar from if you've thought about systolic geometry. In fact, sort of contact forms are related to geodesics, and questions like this are directly related to certain questions in systolic geometry. And there's been some progress on this. So Hutchins and I show that if your 3-manifold has exactly 2 embedded Reeb orbits, then this is actually true. And another interesting case that I've recently been thinking about is where the 3-manifold is what is called dynamically convex. And again, I don't want to go into the definition of convex, but this holds, for example, on the boundary of a convex domain in R4. And the point here is that there's a supporting open book for the Reeb flow. So you can actually reduce this question to a question about area-preserving maps of the disk, which seems to be more tractable. And before I stop, I want to tell you about a big picture reason to think about this conjecture, which is what originally got me thinking about these kind of ideas. And that involves symplectic capacities. So symplectic capacities are ways of measuring symplectic size. And the first examples were introduced by Ekelund and Hofer, although sort of also Gromov in even earlier work. And many symplectic capacities have since been defined. And sort of, roughly speaking, the point of these things is that they obstruct symplectic embeddings. They're quantitative invariants. And if I have one symplectic manifold that embeds into another, then for any capacity C, the capacity of the first is less than or equal to the capacity of the second. So these symplectic capacities. And I'm interested in a family of symplectic capacities that can be defined with embedded contact homology, called the embedded contact homology capacities. So they're symplectic capacities, but I want to point out that they're actually sharp in many interesting cases. So for example, they give sharp obstructions to embedding a 4-dimensional symplectic ellipsoid into another 4-dimensional symplectic ellipsoid. And they also can be used to solve many symplectic ball packing problems. They give sharp obstructions to packing a disjoint unit of balls into a cube, for example. And they also satisfy a volume axiom, which was critical to the existence of 2 Reeb orbits. This type of thing was very related. So you might have noticed, going way back, the dates that Hutchins and Taubes proved the non-degenerate case 3 years ago, and Hutchins and I didn't prove the full case until last year. And the basic point is that one needs to better understand these capacities before one can use embedded contact homology to lift these technical hypotheses. And what the volume axiom says is that for a very large class of symplectic 4 manifolds, those Liouville domains with all ECH capacities finite, then the ECH capacities, which again are a measure of symplectic size, recover this more classical version of size, namely the volume of the manifold, in their asymptotic limit. And again, if you're a non-specialized, think about the case where your manifold is a convex subset of R4. And then the volume is actually just the volume. And these are these strange things which are defined in terms of J-homomorphic curves. They're a lot more exotic. And I want to close by saying what this has to do with the short Reeb orbit conjecture. Well, I haven't given the full definition of a Liouville domain, but the critical point is that it has a boundary. And it's easy to see that any ECH capacity bounds the length of the shortest Reeb orbit from above. So any term in this sequence bounds the length of the shortest Reeb orbit on the boundary, and the volume there, just by Stokes' theorem, works out to a multiple of the volume that I mentioned earlier. So certainly one can't use this to prove the short Reeb orbit conjecture, essentially because we have no control over how this term approaches the volume in its limit. I mean, if you knew that it was, say, monotonically increasing, then that would give you, what you want, more or less. But even still, we know that there's some relationship between these capacities and the volume. So it's interesting to think about if the short Reeb orbit sees this. And I think that's where I'm going to stop. Thanks.